Hello everybody. In this video we're going to be covering section 14.6, buffers. We're going to describe the composition and function of acid-base buffers, and we're going to calculate the pH of a buffer before and after the addition of added acid or base. So first off, what is a buffer? It is a solution containing a weak conjugate acid-base pair. Okay. They are usually prepared from a weak acid or base and the salt of its conjugate pair. Buffer solutions resist a change in pH when small amounts of a strong acid or base are added. So here we have an unbuffered solution with a dye inside of it that can change color with pH. Here we have a buffered solution. If I add strong acid, the unbuffered solution changes pH readily, whereas the buffered solution maintains its pH. Buffers are really important. They're used extensively in laboratory work, and they're very important to biological systems as well. Your blood, for instance, is buffered to maintain its pH. How do these buffers work? Basically, this is a consequence of Le Chatelier's principle. Okay, so long as I have, for instance, acetic acid in solution and acetate ions in solution, if I add hydroxide, I will use up some of the hydronium ions that will create a stressor on the situation. The acetic acid will react with water to replace that, the hydronium ions that were used up. If I add hydronium ions here, that will create a different stressor. Okay, it will react with the acetate ions and push this equilibrium over to the left to use up that excess hydronium that was added. So long as there's some of this present and some of this present, this equilibrium will work to reestablish itself. That does mean that buffer solutions do not have an unlimited capacity to keep the pH relatively constant. It does rely on there being significant amounts of that weak acid-base pair in solution. All right. When enough strong acid or base is added to lower the concentration of either member of the buffer pair, the buffering action within the solution is compromised and they'll break down and start to change pH. This is called the buffer capacity. This is the amount of acid or base that can be added to a given volume of buffer solution before the pH changes. So we can see here what's going to wind up happening is if we just keep adding acid at some point, you can see how the volume has risen here. It's going to break down and start changing pH. Now, an important consequence to understand is that you can increase the buffer capacity by increasing the concentration of the weak acid or base in its conjugate pair. Okay, but you must also maintain its ratio. Okay, you need to have the same ratio of those concentrations as you increase its buffering capacity. If you change the ratio, you will change the pH that is trying to be maintained by the buffer. Okay, so we increase buffer capacity by increasing the concentration but maintaining the same ratio, and we change the pH by changing the ratio of the conjugate pairs. Let's talk about how we would go about making a suitable buffer and what kind of selection criteria we would have. A good buffer mixture should have about equal concentrations of both of its components. This helps you to avoid exhausting one of the components. Otherwise, you're going to wind up with an asymmetric buffer that may be able to take on quite a bit of acid, but wouldn't be able to take on quite as much base, or vice versa. Kind of logically, weak acids and their salts are better for buffers with pHs of less than 7. If you're looking to get a acidic buffer, you want to start with a weak acid, and weak bases and their salts are better buffers for pHs greater than 7. A buffer solution has generally lost its usefulness when one component of the buffer pair is less than 10% of the other. So here we can see that this is what we would call the buffering region as we add sodium hydroxide. And we see that once we're within that 10% region, we're getting to a point where it's going to rapidly shoot up. Okay, that last 10% is going to have quite a bit of change, whereas the 90% before that only had a very small gradual change in pH. There is a very useful equation for dealing with buffers called the Henderson-Hasselbalch equation. I went into quite a bit of depth in the student solution manual about this. You're going to want to become comfortable using this to answer some of the questions on our quiz this week. The ionization constant expression for a solution of a weak acid can be written as this. So we've seen this Ka form before for a model equation. And what we're going to do is we're going to rearrange it to solve for the hydronium ion concentration. After that, we're going to take the negative logarithm of both sides. And then we're going to flip this ratio in order to make it positive. Okay, so that is a property of log functions. We can flip this over and change that sign. Okay, the negative log of Ka we've seen is pKa, and the negative log of the hydronium ion concentration is pH, and now we have pH is equal to pKa plus the log of these two. What you're going to do is you're going to look up the pKa for the acid, okay, and then you're going to put in, this would be the concentration of that salt that you added, okay, the conjugate base, the salt concentration goes here, and the acid concentration is going to go there, and then you're going to be able to find the pH of the buffer. It is important to note that the x is small assumption must be valid to use this equation. Okay, so we need to have a Ka value that is relatively small in order for this to be valid and not have to solve a bunch of polynomials. If you look in the student solution guide, you can see that I derived a similar equation for bases that you can also use.